Welcome to the virtual ICM. I'm Giovanni Felder from ETH Zurich, and this is a special sectional lecture on numerical analysis and scientific computing. It is my pleasure to introduce the speaker, Erik Vanden-Eijnden, from the Courant Institute for Mathematical Science at New York University, who is a specialist in mathematical and computational aspects of statistical mechanics with applications to diverse fields of science. Professor Vanden-Eijnden got his PhD in 1997 from Université Libre de Bruxelles, and his research was recognized by several prizes, including the 2009 Germund Dahlquist Prize of the SIAM and the 2011 J.D. Crawford Prize. The title of his talk is Enhancing Markov Chain Monte-Carlo Sampling Methods with Deep Learning. And I see there is a shorter title today. Please, Erik.
Thank you, Giovanni. Excellent accent both in French and in Dutch, which is remarkable. So I will talk about using tools from machine learning essentially to do Monte-Carlo sampling. And this is a joint work with postdocs at Courant at the time. So the general problem I want to address is the following one. You're giving a scalar evaluate function from a domain omega, which is typically I-dimensional. I'll call it an observable F, and a probability measure, and you'd like to compute the expectation of this observable with respect to the measure. The twist is that the measure is known only up to a normalization factor, meaning that it's given in the form of a prior measure that is simple to evaluate or sample. Think the uniform measure, for example, if omega is compact. An energy U, which then is turned into a Gibbs factor, e to the minus U, and a normalization factor Z. And you can evaluate U pointwise. You can sample from tau, but you don't know the Z. Okay, so this problem arises in a variety of fields, including statistical mechanics and Bayesian inference. In the context of statistical mechanics, this is the U is the energy. This is the Gibbs factor. Typically, the prior measure would be uniform, and Z is called the partition function. And calculating it gives you some thermodynamic property about the system. In the context of Bayesian inference, tau would be the prior, e to the minus U would be the likelihood, and Z would be the evidence that you can use for model selection. So these problems typically cannot be are intractable analytically because the integration is integration in high dimension, and standard numerical quadratic methods are also inapplicable because you're also in high dimension. And so what people resort to typically is Monte-Carlo sampling, which means that you replace the expectation with an empirical average over samples that are drawn from a given distribution. So the simplest way you could think about that, of course, is to try to draw the samples directly from U, but typically the target measure, but typically this is difficult. And so there are two classes of method that have been introduced over the years to do that differently. The first one is importance sampling. The idea is that you generate data independently from a simpler distribution. I will call it a Bayes distribution. You should think about uniform distribution again, or a Gaussian. And then there is an identity that you can use that says that expectation of F with respect to the target can be replaced by expectation of F times a weighting factor with respect to the Bayes distribution, provided that you renormalize things accordingly. And then the law of large number gives you a limiting statement that you can use at finite n to evaluate the expectation. And the weights are simply given by the ratio of these Gibbs factor in the Bayes and the target distribution. That's one class of method. The other class of method, Markov chain Monte-Carlo, where what you do is that you generate a Markov sequence using a certain probability kernel, and it turns out it is easier to construct probability kernel that are ergodic with respect to the target than to sample from the target directly. And so then you use an ergodicity statement simply where you time average your observable along the Markov sequence in such a way that as the limit as n goes to infinity, gives you again by the law of large number the expectation that you desire. And again, you use that at finite n. Now, the difficulty with these methods is that in general, they are not very efficient for the following reason. They come with error estimates. And the error estimate goes like this. Well, when you do the independent samples, typically there's error estimate that you can obtain that involve the variance of the weights. and it's very difficult to control them, typically the variance of the weight will be infinite in most cases, which means that the method is actually not applicable. In the case of the Markov chain, there are no weights, but there's a trade-off, which is that no, they can be very slow decollation time, and that you can quantify using Chemnitz-Weidand CLT. I wrote a version over here, which essentially says that the sample, if your kernel is badly chosen, will decollate very, very, very slowly, which means that the bound that you have by the variance of F as an estimator is typically very far from being reached. Okay, and as a result, the method, when you use these methods, you need typically to tailor the application to a specific problem at end, because otherwise they are not efficient. With the aim being, of course, that either the base or if both the base or this kernel were the target itself, that would be the ideal case, but you cannot achieve that. And so what I would like to do today is to discuss ways by which we could use deep learning, so machine learning tools, to try to maybe systematize the way we construct the identification of the base distribution or of the transition kernel that you use in the Monte-Carlo. Okay, so there has been several talks in the ICM already discussing deep learning. You're well aware of the fantastic advances that these machine learning tools have been providing in the way we process data in high dimension, and slowly but surely they're also becoming more and more persuasive in the context of scientific computing calculation. And the reason is that it seems that these methods are able to process high dimensional data or function better than classical methods, for example, based on finite element. Okay, and in principle, there is, the basic tenet of deep learning make them really well suitable in principle to do Monte-Carlo sampling. Because what do you do when you try to train a neural network? Well, essentially, you use the neural network to represent a complicated task-specific function. For example, the input-output in the game of Go, or what will be the protein that you need to fold here. But here we're going to use it essentially to construct Bayesian function that we're going to use in the context of Monte Carlo. In order to train the network, you need to have a variational principle. This is what people in the field called a loss, which is a variational formulation for the parameters of the deep neural network, right? Then you need to be able to estimate the loss empirically, because typically it's given by an integral that you cannot perform analytically. This is done by training over, so by doing gradient descent over some training data, empirical data, and then you use that to optimize the network by training this parameter by stochastic gradient descent. The reason why I say this is a priori well suited to the Monte Carlo is that if we manage to design proper variational principle for the Bayesian function that we want to use in the Monte Carlo to construct the kernel of the base, then we can use Monte Carlo itself to estimate the loss and its gradient and close the loop in this way. So that's what I'm going to try to discuss in the remaining of the talk. Okay, and I'll do that in the three contexts. I will revisit importance sampling and transport. I will show you how to assist Markov chain Monte Carlo with normalizing flows. And then I will also, time permitting, discuss a little bit about how to do that with other methods that are non-equivalent importance sampling, where their too can be optimized. And for simplicity, mostly of notation, I will focus in the case where the space is either RD or the torus, and the base distribution, the prior distribution is just the bag. And I will denote by rho the densities that are associated with respect to the measure that I'm talking about. Okay, so the basic idea that one can use to construct better sampling in the case of importance sampling is actually to use transport. And so how does that come? Is that imagine that I can construct a velocity field, which is such that if I transport by this velocity field some simple base distribution, at time t equal 1, the solution of this equation is the target. You can rephrase that, this is an Urian statement, you can rephrase that in a Lagrangian way by saying, if you introduce the flow map of this velocity field, it says that if you push forward the base by this map at time t equal 1, it gives you the target. Or if you want to say that even in more layman term, it says that if you draw a sample from the base and you push this sample through the map, it gives you a sample of the target. Okay, so there's obviously a link between this type of problem and problem that arise in transportation theory, except that there is no need for optimality here, and this, of course, has a very long history that guarantee that such a velocity field exists. And these methods have been introduced initially in these papers to process existing data. So if you are given samples and you'd like to process them, right, you imagine that the samples that you are given are in fact samples that are given from the target, and you use the result in reverse, you push the target towards something simple, and then you can go in reverse to actually get new samples. They are generating model. But a priori, even if you have no data, and this is the case that we're going to be mostly focusing on, this is well suited for sampling, since if you manage to construct such a velocity field, then independent sample of your base give you independent sample of your target, which is the ideal case scenario. Okay, so of course, the main question is how do you get V? And then if you follow kind of the tenets of, oh, I think, is this stuck? It's not passing to the next slide. Right, so you need a variational formulation, and an easy variational formulation, or the one that comes to mind, you could use other objective, is simply to use the KL divergence of the target of the push forward distribution by the target. And then you realize that there is a little identity, which namely that if you expand the log, the normalization factor of the target that you don't know goes into a constant, a term that is constant that doesn't depend on the distribution that you're trying to optimize upon. And so you end up having a variational formulation where you simply say, you want to minimize this objective function subject to the fact that you're transporting the density from the base towards this target. And this is a double minimization to this constraint over the rho t and the vt. Okay. And then of course, to do that in practice, you go from this Eulerian formulation into a Lagrangian formulation. So you can simply rephrase it in the following way. This is just rewriting the statement that was on the previous slide using the Lagrangian formulation, which says that you need to minimize this objective function subject to the fact that you are pushing the samples through the map, right? Where this is the Gibbs factor that happened from the distribution, and this is a Jacobian factor that comes about from the transport itself. And again, in this case, what you can show is that all minimizers are such that the push forward by this minimizer of the base is the target, or that you can create independent sample from the target by pushing forward independent sample from the base. Now, once you have reached this stage, well, in principle, you're in business, because you see that the objective and its gradient can be evaluated empirically. I cannot do this integral in practice, and I cannot do it analytically, but I can perform it in practice, sorry, simply by sampling rho b, which I assume is what I can do easily. Okay, and then what the next step, of course, is that you need to do the minimization over a class of function, and this is the place where we're going to use deep learning, meaning we're going to approximate the v of t by a deep neural network, and then you can, once you have done that, you can optimize over the parameters of this network by doing constraint optimization using stochastic gradient descent and adjoint method. Okay, and why do we think that this actually is doable? Well, it's because it has already been done in the field in another context, namely you have all seen these images. People have used similar tricks in the context of generative models where you have data, where what they were doing is you simply take a data bank of images, you push them onto a simple distribution, then you use the map backward to actually generate new samples. And perhaps the most striking example of this has been done with images. What you see here are not actual pictures. They are pictures that are created this way, where you simply train a neural network and then use it in reverse to push noise into these faces, which actually are completely fake. Okay, and so our problem is more complicated because we don't have a data bank of images from the beginning, but we can still sample from the base and then push things forward. So so I'm going to explain to you how to do that in practice. Of course, we also have an advantage that people using data don't have, is that at the end, we can still create perfect samples. And how do you do that? Or you can do perfect sampling more appropriately, is that even if your map is not perfect, so if you don't manage to identify the actual minimizer, this either because the minimization has not converged or because the class of neural network that you use to represent V is not expressive enough, you can still use important sampling, no, not with the base itself, but with the base pushed forward by the map, which amounts to doing the same thing as before, but after passing it to the map, which gives you these weights. Okay, and so if you do that in practice, what does that end up doing? Right, is that, well, you push sample through the base, and then it will train a map that will actually go to the target. And in fact, this method is essentially what was proposed in the paper by Vanden-Eijnden and all, it was in 2015, and this was in the context of Bayesian inference. It has also been used by Frank Noe and collaborators in the context of molecular dynamic simulation. Now, the difficulty with these methods is that they have two practical limitations. In fact, caused by the same thing, is that they have a limited capacity for exploration and they are prone to mode collapse. So you can understand what's happening here, maybe in the following simple term, is that if you don't know your velocity field nor your map at the beginning, you could imagine starting with a V which is identically 0. So the map is the identity. If you do so, you will need, when you try to estimate this objective function here, you will have to generate sample from the base and have enough of them that you can pick a gradient that will tell you in which direction you need to optimize your velocity field to actually find the target. In high dimension, this is very complicated to do. And what typically arises is something that you can already illustrate in low dimension. So what you're going to see here in this little movie that was created by Marie-Lou Gabriel is that this is the base distribution originally. What you will see is how it is evolved as you push it forward through the map that you learn by doing the procedure that's happening here. And if you do that, what you see is that it will actually learn part of the distribution, but the target has two modes and you only detect one of them. Okay, so there's a way to do better than that. And that's the next part of the talk, which is that we're going to use the same principle in reverse, and I'm going to explain to you how to do that in the context of Markov chain Monte-Carlo sampling with metropolis Asting. So the first observation is that if you have any map, an imperfect map, you can use it to perform metropolis Asting Markov chain Monte-Carlo. So what is metropolis Asting Markov chain Monte-Carlo? Is just a standard and by no well-known trick to actually generate a probability transition kernel that is ergodic with respect to a target distribution. And the way you do that is as follows. You propose a new sample from a given distribution. In this case, what we're going to do is that we're going to take a sample from the base, push it through a map, say that this is your proposal, and then you don't accept it necessarily. You only do so with respect to a certain probability that will guarantee that the chain is ergodic with respect to the target. And this is this metropolis Asting criterion, which involve a ratio of quantities that you can evaluate without knowing the normalization factor of all of these densities, right? And so what you do in practice is that given the state of the chain, you generate a new sample and you update your chain to this value according to this probability. And if the criterion is not met, you keep the chain where it is, okay? This, in fact, is the rejection, and that was created potentially the long correlation effect in the Markov chain that I discussed at the beginning. And so you can, in particular, if all of densities that are here are positive, say, and if the map is non-singular, this you can guarantee that this Markov chain is actually ergodic, meaning that you are creating a chain which is such that the time average along the chain gives you the expectation that you want to calculate. There is no need to reweight, and you get independent samples if the map that you have constructed has the property that it pushes forward the base onto the target, right? And of course, you can combine these things with other metropolis Asting. You're not obliged to only do this. You can, for example, use more standard technique like metropolis adjusted Langevin algorithm to create sample, then from time to time do resampling step like this. So this is sampling. But then there's a training, and the training, well, we can use essentially the same variant as what we used before, but in reverse, which is, so I'm going to just flash it by you. The idea is that you change the role of the base and the target. And so now your objective function is an expectation with respect to the target, right? And what you're trying to do is to push the target backward towards the base. Okay, so that's what you optimize the map doing that, and then you use it in reverse. Okay, and this can be done because you have the chain is actually giving you the data that you need to do this sampling. And so if you see what happens in practice, right? So you have the data that is estimated by the MCMC. What you need to do, what you need to have to make this method work is that you need to have a rough location of the mode to start the sampling. So there's no free lunch. You need to know where they are, but you don't need much more information. You just need to know more or less where they are. And what happened is that the sampling is actually then training the map onto going into these over these modes. We show you what happened with this example again. And you never need to have a connection in real space, like you would do, for example, if you use umbrella sampling, to actually get the relative weights of these. They will be learned through the learning of the map. Okay. So, for example, if you do this the same little movie, you see that if you redo it with this method, you see that now it's going to learn the two modes. What happened is that the only information we had is that one sample in each mode. So that's their rough location, but they have very different weights, and the weights are learned along the way. Okay. So of course, these are very simple examples. Let me show you. So in practice, what you do, let me first say that, is again, just repeating, you perform metropolis asking Monte Carlo that alternates between local sampling region with Mala and then resampling step with this normalizing flow, the map that they have described. Okay. And this is used to generate the data. You use the generated data to train the neural network. And then you use the trained neural network to get more data, and then there's a feedback loop on this. So let me show you maybe quickly a few examples. Right, so, okay, before I say that, sorry. I'm not going to discuss this. You can analyze the conversions of these methods under, specialized conditions. They are typically hard to analyze because they are what's called nonlinear MC method, nonlinear in the sense of McKean, in the sense that these are methods where the kernel, the probability, the transition probability depends on the law of the process. Okay, but there are methods to analyze this, and in certain cases you can actually show conversions of the method, though it's much harder to show conversions rate. So you can prove conversions, whether it actually accelerates or we know that it will accelerate, but by which factor, that's more complicated to establish. But let me show you a few examples, maybe to illustrate that you can actually do this in high dimension. So this is perhaps a simple example. So you're looking at the Gibbs measure that is associated with the 5-4 energy. That's the problem Martin has worked a lot on, but we are looking at the simplest case, which is the one-dimensional case where everything makes sense with auto-normalization. And so the measure that we are looking at is the one that's associated with this energy, is an exchange term here, and then there is a potential term here, which is bimodal. So this guy wants the field to be at plus or minus 1. You look at this measure subject to Dirichlet boundary condition, and so the typical sample that you get are shown in blue. There is bimodality. They are either a bridge that go by the up, by +1 or by -1. Okay. And so in this setup, what you can do is that you can take as base distribution simply the Brownian bridge. So you drop this term, or you replace it simply by a quadratic term. That's not easy to sample. That gives you the sample that are in black. And then you train a map to actually take one of these Brownian bridges and map it onto something that is supposed to be from the distribution, the target that you have, and you can learn such a map. It's a complicated map because it's a map that is strictly speaking from a function to a function. In practice, we did it here. The example that I show is with 100 spins. So it's a 100-dimensional map. And what you can show is that the model is trainable. So in black here is show the log likelihood, which is going down to 0. And in blue, what is shown is the acceptance ratio that you have in your metropolis asking. So as you train the map, you get more and more acceptance, which means that more and more you can take one of these samples and push it directly onto these, a sample that is a sample of the target that will be accepted in your metropolis asking Monte Carlo. Okay, you can do the same thing for similar models that are otherwise difficult to sample. The archetype is a model that I have first order phase transition. Here is one. It's a model of particles that interact through a short range potential, which is pairwise. It's written here, n particles in 2D in this case. Okay, so this model was written it's a simple model because it is in a mean field limit. So there is a mean field description that you can have, meaning that in the empirical distribution of the process, satisfy a minimization principle in the limit when n goes to infinity, where there's an energy term that is directly inherited from the energy that was there, but you gain an entropic term due to the fact that the particles are indistinguishable. You can interchange them. And so this model has a phase transition simply because the entropy term depends on the temperature. And so at low temperature, the energy wins, but at high temperature, the entropy wins. When the energy wins, you get a cluster. All the particles tend to collapse into a cluster. It's a liquid-like phase. But at high temperature, the entropy wins, and so you get something which is uniform. And now, if you look at the minimizer of this free energy, you realize that there are two branches that persist in a range of value of the temperature. This is indicative of a first-order phase transition. And what you really would like to identify is the point where one phase, this one, say, becomes more likely, more thermodynamically stable than the other. If you try to do that by sampling, standard sampling is very difficult, because if you initiate, say, Mala or Langevin dynamics, if you wish, from one of these configurations, it will stay there forever. If you initiate it here, it will stay there forever, so you will never know what is the relative weights of these two states. But if you learn a map that actually use this as a base and try to push it forward over there, you can actually learn the actual weights, and that's exactly what is happening here. And you see that the map identifies, there's the parameter of the map that go from plus or 1 that tells you whether it has identified the phase transition. So these things work. Okay, maybe a third example, briefly, which is more, not from physics, it's from Bayesian inference. So this method is also applicable in cases where the likelihood is complicated, for example, where it's multimodal, in which case, if you do minimum likelihood, maximum likelihood, you have multiple basin, and then you need to find out which one is the most likely. So a simple example of that is an example that we borrowed from my colleague in physics, which is about inference of exoplanet radial velocity. It's actually a toy, so let me just explain. It is not with actual data, it's synthetic data, but the model is actually quite simple. You are given a certain number of points of a time series. These are the red dots, and you need to put a sinusoid through it. You don't know the amplitude, you don't know the phase, and you don't know the period. Okay, there are more parameters than that. In fact, there are 6. And so, as you can see, if you have little data, there are many minimizers of the likelihood, and you need to identify which one is the best. And so here too, what you can do is that if you know roughly the location of these minimizers, you can start to do sampling, where again, you sample, the likelihood goes down and the acceptance rate goes up. And so at the end of the day, you can identify which one of these is most likely given the data. Okay. Right. Okay, so now for the remaining maybe 10 minutes, I will describe what one can do by going into something which is maybe a little bit more elaborate, which is what I have discussed here is in principle equilibrium sampling. There's a non-equilibrium aspect to the method because there's a training, but now we're going to make this non-equilibrium aspect even more prominent because we're going to use non-equilibrium sampling from the get-go. So I'm going to start with a little proposition that was proven a while back, which essentially by Roscoff and myself, which essentially says this, it's an identity, which says that if you give yourself a map, this time time independent, and you compute the time average of the observable with respect to this map, the time average is defined in this way, okay, where J is just the Jacobian of the map. Then if this time average converges at the limit of t goes to infinity, in fact, this limit is not necessary. I'm just using it because statement is simpler to state this way. Then there's an identity that says that the expectation of F is the same as the expectation of the time average of F, where the time average here is constructed from a given initial data. Okay. Okay, so it's a little bit, right? A couple of comments to try to understand this, and you'll see more of that later. This is not an ergodic average. You can do that at finite time, and as you will see, the trajectory here that we are using through this map doesn't visit the whole state space. Okay, and you can think about this essentially as being an important sampling estimator that uses a family of map instead of a single map, right? And why do you think a priori that this might be useful? Well, it might be useful because with the proper choice of the velocity, even though you have this identity, if you base an estimator on SF, it might be better than basing it directly on F. Recall that in practice, to estimate this expectation, you need to draw sample from the base, and you have only a finite number of them. And so it could be that the variance of this is better than the variance of that. And why do you think that that might be the case? Well, it might be the case if, for example, the base distribution is concentrated in some part of your domain, but the function that you want to take the expectation of as a support that is very separated from it. So if you do the naive method that is based on this, your sample have no statistical significance with respect to expectation that you want to compute. But if you manage to push this sample in the right direction, you can expect that they will have a better properties in terms of the variance of the estimator. Okay, so you may ask yourself, well, how much? Well, there is a result which actually is, I think is quite remarkable because it's a little bit surprising, that says in fact that you can build ideal importance sampling estimator. And so the result is like this. So I'm going to focus on one specific case, which is the calculation of the ratio of partition function. So suppose that I have a Bayes distribution that is simple, think Gaussian again, or uniform, where I know the ZB, and what I would like to calculate is Z. Then there is a simple identity that tells you that the ratio of Z and ZB is in fact the expectation with respect to the Bayes of the ratio of the Gibbs factors. Okay. This identity is not useful in practice, even though it's true in general, because the estimated bases like that are typically infinite variance. These are in fact the weights that we saw in one of the first slides. And so you cannot use it directly for the same reason. If this density is peaked in one region of space and this one in another region of space, which is the rule more than the exception in high dimension, you will get infinite variance. So you need to do something which is better than that. And the interesting result, it says that for this problem, there exists a velocity field, which is such that the estimator has zero variance. We mean that for if you solve for the velocity field by solving this Poisson equation here, if you pick any samples and you pass it through the time average, you get the ratio for any one of them. So let me try to explain that through a picture so that you also see that this is not the ergodic average. Imagine that the Bayes, we take the two-dimensional torus, imagine that the Bayes is just the uniform distribution of the torus, and imagine that the target is this three-modal distribution whose level sets are shown underlying here, okay? If you solve the Poisson equation, which one can do in this case, you end up having the potential which is shown over here. The level sets are shown here. And then if you look at the flow lines of this velocity field, they are the lines that are identical that you see on both pictures that always go from the red dot to one of the green dots. Okay. And what the statement says is that you can pick any point in the torus and do the time average over one of these trajectories, say the one that the cursor is a little bit big actually to show, but they say the one that goes through here. And that will give you the right value of the ratio of the partition function for one guy. Okay. Now the question, so this is an existence statement, but now you can use it by saying, well, let's try to learn this V using the similar technique that the one that I've explained before. And so how can you do that, right? But maybe before I say that, there are connections between this problem again and optimal transport. I'm not going to discuss that. There's also connection between this problem and Beckman transport, and I'm not going to discuss that, but all of these things can be, the references are given here, and there's a lot of information in the book by Cedric Villani about this, and there's another book by Sant'Ambrogio, which is fairly accessible. So how can we use this in practice? Well, remember that I don't know the Z, but I can, so there's one statement that I can make, is that first I can use a variational formulation of the Poisson equation, which is expressed in terms of expectations. And so this is a loss that in principle I can use to learn the potential that I have here, because I can estimate it empirically and represent the phi again using a neural network. What I'm going to show you is something which is in fact more direct, where we simply use since we want to minimize the variance of the estimator, you can simply use the variance, which since it's an unbiased estimator, you can simply use the second moment of the estimator as objective function. Here it is. Okay, so you use this as an objective function, where again you can sample it in practice because you assume that you can sample from UB. So if you do that, right, concretely we do something which is slightly different. We use a finite time variant of the estimator that I showed you. It's possible to write it down. We lift the requirement that the velocity is the potential, because that we know that there is an optimal velocity in this class, but you don't need, it's not necessary. And then you use the objective function as an objective function for the parameter in a neural network that you use to represent the velocity field, using, again, borrowing from what has been done in other fields like generative models, right? And then you can estimate the objective function and its gradient using sample from the base and an adjoint method to enforce the constraint that the velocity and the flow are related in this way. Okay, and so I'm just going to show you a few examples that tells you and show a bit what the maps are. So if you can do this in high dimension, for example, with Gaussian, these are a mixture of Gaussian. I'm just showing you in 5 and 10 dimensions. I'm showing you projections. If you learn a velocity field in a class of neural network, what you end up having is that, so I'm projecting here what you see, is that you end up having flow lines that are the white line that are here, and they terminate because we use it at finite time. Okay, and then you can ask yourself, so these are all cases where the naive estimator would have infinite variance, and you can see that after training, these are these columns, you end up having estimators that are not perfect. You never achieve the zero variance estimation, but they have a variance that is very, very small. Okay, and we compare that to several things. One is what you do if you try to guess the velocity field. There are ways you can get. That's what we are doing in the original paper, and you see that it works much better. And we also tested that against the method that is actually standard in the field of non-equilibrium sampling, which is called annealed impulse sampling, introduced by Neal, where what you do essentially is that you're also constructing a map, guessing a map, but it's done in a slightly different way. There is no optimization in that case. And there too, you see that you get estimators that have a much bigger variance or even bias than what you can do with these type of techniques. Okay. Again, to be fair, there is no optimization here. This is just showing you the advantage of combining sampling and learning, which is the objective of the talk. Here's an example that is taken from Neal's original paper. It's a funnel example. It's an interesting example because it shows that in high dimension, sampling, can be problematic, not because there is bimodality or metastability, right? But simply because there's a lot of space, there's a lot of entropy. So the model that he used to show that is that it's a 10 variable, where the first one is just a Gaussian independent of the other, and then the 9 other are Gaussian conditional on this one, with a variance that depends exponentially of the first variable. So if you think about this in 2D, right? If this is x2 and this is x1, the variance of x2 shrinks exponentially when x1 is negative and explodes exponentially when x1 is positive. Okay, and again, if you try to calculate in this case the ratio of the partition function using as base distribution, say a unit normal, a Gaussian for all variables, the variance is infinite, right? And so this was the example that Neal used with important, annealed important sampling. If you train the map, you get this, and you can train the map to again get very, very low variance. This example is interesting because in this case, if you think a little bit about it, you're not obliged to learn into complicated classes of velocities. You don't need to use deep learning, even though you can. We did, that works. But you can also simply use linear type velocity field with a vector A and a matrix B that you need to learn. And that works just as well. And this is what it gives here. Okay. Okay. So let me see. Right. I think that this brings me very much to the end of my talk. So what I've tried to explain to you is how tools from machine learning can allow us to revisit certain problems of scientific computing by using the expressive power of this neural network. And that's something which can be done in many, many different areas than the one that I described here. I just described it in one specific case because it's one that seems to be really tailored for it, which is in the context of Markov chain Monte-Carlo or Monte-Carlo sampling more generally, because it has the advantage that you want to learn a high dimensional function, but even if you make an error on what you have learned, you can always correct things because you embed them into an important sampling or a Markov chain Monte-Carlo that at the end gives you the exact truth. Okay, and so I try to explain to you, how this has been made possible in this deep learning technique. Of course, I listed a few mathematical questions that are interesting, which is to try to understand what is the convergence property of these methods, etc. But there is clearly, a big elephant in the room, which is, something that has been discussed in some of the other talks in machine learning, which is that this relies on the expressive power of these deep neural network and our capability or ability to train them. And even though there's a lot of progress that has been done in recent years into trying to understand this issue better, it's still very much of an open problem. And so, the state of affairs here is not yet at the level of standard numerical analysis where we can give a priori error bound or error estimate, because actually we don't know really what is possible to do with deep neural network. In particular, we don't know what is the approximation error, as I just mentioned. We don't know when we use stochastic gradient descent algorithm, whether we have conversion guarantees. Can you actually train these networks? We don't know what is your generation error, because you're always training this on a training set. In this case, it's online learning. Your training set is growing, but you always want to use it outside of the training set. So that's called the generalization error, and we don't understand that very well. And so these are all, I think, fantastic mathematical questions that are, open problem of the field, and very interesting one, because clearly there's one thing that is certain, is that in practice, these methods actually work fairly well, as, your phone is telling you already with all the capability it has, but certain calculation also show you. Okay, and with that, I thank you for your attention.
Thank you very much for this beautiful talk.
From this lecture. Matti.
We would have time for some question, right? Maybe there is a question in the audience.
Yeah, I was wondering, so in the examples you gave at the beginning, you're always trying to push a unimodal distribution onto a multimodal distribution. So I guess the map, so for example, in the second example you gave, there was some sort of little umbilical cord that remained, right? So your map would have to kind of break up that unimodal distribution in some way. So do you have any kind of impression of how that breaking usually happens? I mean, like in the more complicated cases, so I'm thinking about the Brownian bridge that gets mapped onto that 5-4 measure. Like, how does it decide, like, so, which bits get mapped up and which bits get mapped down?
So it's very, very well spotted. In principle, in the velocity class that we learn, they cannot be singularities, which means that they will remain connected, right? So there's two, things that help you. One is, as I explained, even if this is the case, the map doesn't need to be perfect, right? The mass that there is in this filament for this example, for example, is negligible. And so, you use that. But more generally, if you know that you have a multimodal distribution, it would be probably better to use a multimodal base, because then you don't, you can just push, right? And that we have done. Now, the question is, how much prior information do you want to use about the distribution, the target, to do the calculation? In practice, you will use as much as you want, right? But I was trying to show what happened if you use as little as possible. But indeed, this shows that there are these little problems. It's difficult to construct map that would be perfect.
So, Eric, could you move 2 meters to your right? We don't see you on the screen.
Oh, sorry.
I think we still have 2 minutes for a question, if there is a question from the room.
Yeah.
Okay, maybe this is too general question, but is there some characteristic of the computational problem where you can apply the deep learning techniques?
You mean in this?
Oh, no, in general.
That is part of the open question. I mean, there was the talk of Wayne and there were other talks in the conference. Mm-hmm. This is really, an open topic, right? And it's one that is actually where I think that applied mathematics, and that's also something that echo what the other speakers have seen, I think, where applied mathematics in general, can help a lot in scientific computing, because the difference that we have with respect to the problem where these methods have been applied, like, for example, image generation, that we have a ground truth. Right? If you do classification of cats and dogs, it's not completely clear what is the function that represents a cat or a dog. So there's no ground truth. But here, we can, in principle, assess, right? We know what is the velocity. So in toy example, for example, if you go between, you construct map between a Gaussian and mixture of Gaussian, you can sometimes construct the map analytically, like you have, then you can actually ask yourself whether it's possible to represent them in the function class that the neural network learns in. So there is, there is ground for progress. That's what I say. But do we really understand? If you tell me this is my problem, I want to do a problem, in molecular dynamics with a complicated distribution, or this inference problem, what neural network should I use to have guarantees of conversions, accuracy, etc.? I think by and large, at this stage, this is an open problem.
Okay, thank you very much. I think we are at the end of the allotted time. Thank you also everyone for joining it, and please enjoy the rest of the ICM. Bye-bye.